Dark matter. What is it? Where is it? And how do we know it's there?
What is it? The book defines dark matter as matter that we infer to exist from its gravitational effect, but from which we have not detected any light. Dark matter apparently dominates the total mass of the universe, also thought to be continuously expanding and created with the Big Bang. Dark energy makes up 69% of the universe, while dark matter accounts for 26, leaving only 5% for baryonic matter, the matter that we interact with every day. Dark matter is also 50 times more common in galaxy clusters than standard galaxies. That means that our own galaxy, the other galaxies, star clusters, and everything we've ever viewed in space makes up only 5% of the universe. Dark matter and dark energy are easily confused, but dark energy is a force known to drive the expansion of the universe, while dark matter is the matter accounting for the mass missing in space.
How do we know it's there? In 1933, Fritz Zwicky was the first person to discover dark matter. When doing calculations of the gravity and the mass of objects, mass is missing, therefore leaving something unseen. That's how we came up with dark matter. It also interacts with visible matter through gravity and also through gravitational lensing, distribution of matter between a distant source and a viewer. In essence, the evidence of dark matter existence is almost undeniable between the continuous calculations that come up with missing mass from galaxies, dating all the way back to 1933.
The different types of dark matter. Cold dark matter is free moving particles much smaller than a protogalaxy, which is a gas cloud that has potential to become a galaxy. Warm dark matter is particles with a streaming length quite similar to a protogalaxy, while hot dark matter is particles streaming with a much larger wavelength than a protogalaxy. Note these comparisons have nothing to do with actual temperature, being that we can only theorize about dark matter. We don't have any idea about any temperature for it.
Current dark matter theories. Earth may have long hairs of dark matter. Propose the idea that Earth is surrounded by strands of dark matter. If this proves to be true, it will give great insight into what dark matter is. Astronomers and astrophysicists would be able to consistently study and monitor dark matter. This breakthrough could give scientists a precise and consistent makeup for what dark matter is and its other properties, which could possibly lead to other breakthroughs in our knowledge of the universe.
Dark matter makes up about 27% of the cosmos, but so far no one knows what it is. Dark matter neither emits nor absorbs light, and it interacts with the rest of the universe, primarily through gravity. In fact, it's thought dark matter traced the initial framework of the cosmos, attracting normal matter that forms stars and galaxies. Black holes are astronomical objects famed for their extreme gravity. Jeremy Schnittman, an astrophysicist at NASA's Goddard Space Flight Center, wondered if they could serve as a kind of laboratory for exploring different dark matter models.
The leading particle physics model for dark matter is called weakly interactive massive particles, or also known as WIMPs. These guys just fly through the universe without even bumping into anything or each other. The idea of two WIMPs coming together, annihilating and forming gamma rays, is kind of like two bullets hitting head on in a crossfire. It's very rare. But when you do go to the area around a supermassive black hole, we expect the density to be much higher, so the probability of annihilation is much higher, and thus detection with gamma ray telescopes.
In Schnittman's computer simulation, a population of dark matter particles orbits a rapidly spinning black hole. Close in at the brink of the black hole's event horizon. The particles are orbiting at nearly the speed of light. The lighting shaded region farther out is the argosphere, a zone where all particles are forced to move in the same direction as the black hole spin. The concentrated dark matter collides and makes gamma rays. But not all the light can escape from the argosphere. The gamma rays most likely make it out come from the left side, where the black hole spins towards us. The result is an asymmetric glow. The highest energy gamma ray comes from the center of this region, corresponding to the black hole's equator. Snitman's work has uncovered previously overlooked orbits that can produce extremely energetic gamma rays, and has shown as the peak energy attainable for the escaping light is strong function of the black hole's rotation. So far, the initial work is focusing on setting up upper limits on the dark matter annihilation rates by looking at otherwise quiescent galaxies, but Smitman's ultimate ambition is nothing short of an ambiguous detection of dark matter.
To me, dark matter, black holes, two of the most elusive things in the universe coming together to help explain each other is quite poetic.
WIMPs, or weakly interacting massive particles, which are subatomic only massive as compared to other lightweight particles such as neutrinos. WIMPs are thought to make up 22% of the mass energy of the universe. This looks to be a promising theory of dark matter. WIMPs cannot produce photons, which would explain why dark matter emits no light.
The MOND theory. The MOND theory, an idea proposed by Morty Milgram that instead of dark matter existing, there is a slight change in the effect, force law at low accelerations, is thought in experiments and tests that Einstein's theory holds up, but possible changes occur in a large space like a galaxy. This theory accurately predicts dwarf galaxy textures, often credited to dark matter. All before any observation took place, it recently accurately predicted the motions of 10 dwarf galaxies orbiting the galaxy Andromeda.
The string theory. Theory of quantum gravity that states that everything is made up of tiny, tiny, tiny strings. And these strings vibrate when stimulated by an outside force.
Expansion of the universe. Dark matter is thought to be closely related to the expansion of the universe. A decelerating universe reaches its current size in the least amount of time. The universe could eventually contract and collapse into a big crunch or expand indefinitely. A coasting universe, center one, is older than the decelerating universe because it takes more time to reach its present size and expand forever. An accelerating universe, on the right, is older still. The rate of expansion actually increases because of a repulsive force that pushes galaxies apart.
Gravitational lensing, dark matter, and Einstein's theory. Einstein's theory states that the pull of gravity is actually just bending of space. Large objects distort the essence of spacetime for near objects, much like how time moves slower in a black hole, because it affects spacetime so much. This distortion accounts for changes in movement of other objects.
Here's some popular dark matter simulations. And finally, our citations.